Yep.
Next question. What is your favorite?
Oh God. What? No, yeah. Okay.
Your overall favorite word?
Tricky.
You talk about
Tricky.
words nonstop.
Tricky. Yeah. Yeah. It's true. When I was a kid, I really liked the word lull.
Lull.
Yeah. Which I could say repeatedly, kind of an ADD type way to my mother's great disappointment. It just feels really good to say. So the important thing is to say a word over and over until the meaning goes away, and then you get the bare feeling of it, and then you can go back to having a meaning. Yeah, I had that post, right? Yeah, Speakfeel. Speakfeel. I call it Speakfeel. Yeah, how a word feels, how they taste. No, I had a whole bunch of old friends writing about that because I posted something about it. So ointment was someone pointed out they like ointment.
Not my choice.
Not yours. Yeah. There's some words like monthly and plinth, which are just kind of fun to say because it's got that L and all the approximates going on, right? The plosives are good, so you gotta have boop, boop, you gotta have some stuff like that. So flux capacitor is good. So that elicits some good memories as well. Yeah. Right.
I poem that the most poetically perfect phrase in the English language is Salador.
Is what? Salad?
Salad, like a basement. Salador.
Salador?
Yeah. I think my favorite will be Costless Stylus now.
What is it?
Costless Stylus, like the Costless Stylus space nutrition. Next my mama.
Okay.
I thought it's like
You forget the meaning away from it. You forget the meaning. Yeah. Well, it's fun just to think about all the sounds you can make, right? And it depends on the phonemes of your particular language, but where they come from. So, and come out of your nose, right? And you block them. You block your mouth in different places with your tongue, and they're fricatives. And then and so they're labiodental because it's here. You have to, and the way that, so you say something like k or g, and you hold it there, and then breathe back in. So some of them are easy, like s and z. And you can feel where the air is cold, or where your mouth is cold, that's where it's really doing the work. And z only differ because your vocal cords vibrate. So they're voiced and unvoiced things. So t and d are pairs, t and d, they're absolutely the same except with your voice box. So there's a whole bunch of those, right? B and p, and b and p, they're plosives, they explode out. You can't keep saying but it's all over. And then there are these other ones like Africa, it's like j and sh. We should, so again, pairs, right? K and g are back in here. And then there's vowel space. And it depends where you're from, right? I, for igloo, I. And they all get moved around a little bit. So New Zealanders say, pun and 1, 2, 3, 4, 5 sucks. Fush and chops. Who knows what they're doing? Yeah. And then the Scots, well. Yeah. I once had a Scottish woman say, it's talking about US people not being able to understand her, and it took me 30 seconds to understand it. That's what she said. Like, yes. I have to say, train spotting, we saw that I saw that with a couple of Australian friends in Boston years ago, when you may not have seen this film, but they say some very bad words in that film, but you cannot understand it. Unless you're really into the language. And we're sitting in this theater, no one's sort of registering these things they're saying. There's dead silence, you're with us. Anyway.
I love it when you see a Scottish person in like a documentary.
Which they did in Train Spotting, I think. In the this is a long time ago, but in the nightclub scene.
Yeah.
They thought it was too much even.
Some people think that the language of Lower Scotland is its own language. It's not even English, it's Scots.
Yeah, well, I had a chance to sort of out. I was going to, yeah, they were great words. I mean, just great. Really fun words to say. And then terrible. So, pulchritude. One of the worst words you could ever imagine. It just sounds bad. It's Greek origin, but it means beauty. I mean, what a terrible word. Pulchritudinous. You are looking pulchritudinous. It's the correct answer, but you feel like, I know I've crossed the boundary there, but you know, like it feels, it's hideous. So let me stop this. So I call it, so pulchritude, and onomatopoeias, right? Sort of. So there's words that don't sound at all like they should. Yeah, right. That's a good one. There are a few others like that. Yeah, I don't know what it is about lull. It's just not. You really get out there. Oh dear. It wasn't lull. It was different to that. Okay, so all right. I'm happy to talk about words all day, actually, but this is so. I'll try to show you some more. Usually, I show more things at the start of lectures, and so Nautilus is a new magazine about science. Actually, they print things, but everything's online. There's a quarterly piece that comes out. Really nice. I mean, I had a piece in a couple of years ago. We'll talk about that at some point because, I can't help myself. But these are. So this is a really interesting. So it's got all sorts of things, right? There's all sorts of. There's a theme for it. So what's the theme? There's usually a theme for each quarterly. So this is something to do with. Is it facts? Is that what's going on with this one? I'm not sure. But this is about Krakatoa. So the decibel rating was 172 apparently. This is with the estimates later on. Of course, this is 1883, is it? Yeah. And we know a lot about it because people had instruments all around the world, so they actually picked things up. And the crazy thing is, this was experienced 1,000 miles away. So there's where people actually heard Krakatoa exploding. I mean, it ripped an island apart. So it's here in Indonesia, and halfway across Australia, people actually heard. They sounded like they thought it was artillery in the distance. And this is insane. And then it passed out of our hearing, but there are registered, pressure wave disturbances that suggest that it went around the Earth 4 times before dissipating, which is bananas. I mean, it's going like this around itself. And just shock. I mean, there was a boat of English, usual kind of story. The English are floating around somewhere in tweed jackets, trying to, conquer lands and so on, with a whole boatload of cutlery and a library and stuff like that, and bow ties, and say, very, very good, we'll have that. And most of them die, of course, which is sort of good. They're halfway up, or a long way up, places like Mount Everest. You find an Englishman in a tweed jacket. The Dutch were pretty good with Australia. It used to be called New Holland, actually. Right? The Dutch were kind of doing well with this whole conquering lands business. They had New Amsterdam, and this was New Holland. They sold that, but there are a number of Dutch explorers who thought they'd find some water in here. Did not work out. So there are some. There's some, and Van Diemen's Land, right, and of course New Zealand is right. There's Old Zealand, which is in the Netherlands, and then New Zealand. Anyway, Van Diemen's Land became Tasmania. So, yeah, this is unbelievable. It's just unbelievable story. It's crazy to read. It's beautifully written, and it's just amazing how big that was. And it's apparently, I mean, we know, I guess, it's the loudest sound that's, there hasn't been a louder sound on the Earth since then. And you'd probably have to figure out going back in time. But we had enough instrumentation to see how this thing traveled around. And, people sitting there watching their instruments. Anyway, yeah, here's this guy. The eardrums of half my crew have been shattered. They're only 40 miles away from it. There you go, British ship. He's convinced the day of judgment had come, which, I mean, fair enough. I mean, it's insane, right? So a jet, if you're sitting next to a jet engine, it's 150 decibels. 10 decibels is it's increasing the noise level by a factor of 2, right? So it's twice as loud as that, and then twice as loud again. All right, there's an article for you. I mentioned this is completely random, but I mentioned this robin the other day, and we have bird fanciers in the So I showed you the little bird thing, right? Let's find this guy. This is 7 seconds long.
Sure, you can wake me up.
He's sleepy. Dopey little thing. And this is why we looked after this character at night, because it was pretty clear someone was going to eat him. or her. Oh yeah, come on, chirp. Oh, we want to hear the chirp. Yeah, there you go. Instant replay. So we got to recognize the sound of this character, right? So it started to make better noises after a while. And my eldest daughter called this one Tsubasa, which she's a Japanophile, so which means wing, from what I understand. And so here's an extra bit that I showed you this. So it grows up, and it's all very good, and the mum and dad come and feed this bird over and over, and then eventually it flies away, right? And it keeps going to the neighbor's yard, and where there are sleepy cats lying around, so we just sort of bring it back. And then eventually it gets big enough and it flies away. So we don't see it for 2 weeks, it's gone, we're like, we did our job, we helped the bird, but it's sad because we miss our little friend. And then we hear the noise, we hear the sound, right? So I'm like, oh my God, so the bird is there, right? So I go outside the house and I'm walking around the side of the house, and I can see the bird, and it's like bouncing away, kind of looking back, and one of the parents is there and it flies off, and I kind of go towards it saying, hey, what's up? And then this is the crazy thing. A chipmunk appears over here, and I'm like, oh, chipmunk. This is so cute. It's very cute. Everything is cute. It's chirping. There's a chipmunk. They're so cute. And then the chipmunk just goes boom, and takes out hammers the bird. It's like a bowl of chipmunk and feathers. And I sort of run, and I'm like, no, I think I said, you bad chipmunk. And it runs off, and it turns out chipmunks will take out. No one knows this. Everyone thinks chipmunks have got this whole story going on, that they're cute and you should look after them. But they will eat little, right, baby birds.
Yeah. And squirrels too.
Squirrels too? You think they're eating nuts and so on, but they're like. Anyway, so that was kind of a shocker. So that chipmunks, evil little characters. There you go.
Deer will do it too. Like deer will go to the nest and eat the baby birds and eggs.
Wow, this is just destroying everything I thought about Bambi and. Okay. All right, there you go. There's a little warm up. We're easing off a little bit here. So, okay. Yeah, we can talk about birds and words. All right. Take it by bird, oh, there's that line, right? Take it bird by bird. Take it word by word, bird by bird. All right. Okay, we're going to talk about complex networks. Oh yeah, so networks. So that's the new framing, right? So there was axis of evil, which is this very kind of mechanical one line. So there's an axis and it rotates around it. What is it called now? The network of. Obama said this. The network of. I've forgotten. It's the axis of evil. Now it's the. What do they call it? The network of terror or something like that. It's not evil. Anyway, it's a network story. You can look this up. So they're elevating the rhetoric into networks. Okay, which is what it is. Okay, so we started to talk about the properties. Yes.
Network of death.
Oh, network of death. I mean, really, that is some wordsmithing right there. That's fantastic. Yeah, that's good framing. Buzz frame. I call it a buzz frame. Actually, it's a buzz frame. It's hard to kind of think this is about a nice thing. All right, okay. Let's talk about things. Network of death. All right, so networks, so complex networks, good and bad things. So we went over this, and you'll eventually get a problem on this sort of thing. So degree distribution is the big story for networks. It took a long time to figure this out, but it is the way. So we'll come back to this later on, particularly when we talk about scale-free networks. That'll be the story there. And we'll see that this was missed by everyone, including the small world people, which is fine. I mean, obviously it was hard to find. Okay, so we've got these things, and then I got up to assortativity, and we talked about that. So that's that there may be, so you look at these networks and they have correlations in them, right? So there's some tendency for things to, that are similar to each other in some way, and we have this idea that, we could look at the degrees, the number of friends that nodes have, for example, is a very simple starting point. But it could be anything. It could be the age of the nodes. It could be, if it's people, it could be their social, their preferences of, all sorts of preferences they might have that line them up with each other. And, age, of course, puts you into cohorts. All right. So lots of reasons why there may be some kind of sorting or, anti-sorting within networks, and it's a very natural thing to look at. Okay, so clustering is another big piece. So we've got degree distribution, hugest bit, and then we've got all these extra pieces, which are somewhat, they're hard to sort of see how they, your sortativity is one thing, and they're just all these sort of categorically somewhat different things that we seem to have uncovered as being important and debated about that. All right, so clustering. I don't know if you can do a little problem here, but let's think about this. So we start on this. So we have a center here. We have a node A, and some of A's friends are friends with each other. All right, and there are a couple of ways to think about this. So we'll dig into these a little bit. So the first one comes from Watson-Strogatz. This is the famed Small World paper, the one with 25,000 citations. Oh my God, which is insane. Okay, and this structure here, just to repeat, this little a is an entry in the adjacency matrix, which records the weights of the connections between nodes. So A, J1, J2, so J1 and J2 are labels of nodes in the network. So in this case, it's binary, so it's 1 or a 0. So 1 if they're connected, 0 if they're not connected. So for C and D, it's a 0. For C and B, it's a 1. So this is simply a counting thing. This is a mathematical way of saying, let's count the number of friendships that actually exist around A, right? Because we're looking in the neighborhood. This is the neighborhood of I. And on the bottom, we're going to count the number of possible ways. And so it's a binomial. It's k choose 2. K sub I choose 2. Degree is not generally indicated by k, pretty much universally, actually. So k times k minus 1 divided by 2. That's the number of possible pairs. All right. So this by itself for one node is it ranges between 0 and 1. So it's 0 if none of your friends know each other, 1 if they're all connected, and then you average over all the nodes in the network. That's what we'll call C1. So that's a measure of clustering. So it's a measure of the socialness of the network. And it doesn't mean it has to be to do with people. I mean, you can talk about protein networks being social and so on. We just say whether it has a high degree of clustering or not. But it is trying to get at, it's a nice way to think about it, is socialness. And then here's a more graph theoretic kind of approach due to Newman, which you'll see people use either way. But this, there are a lot of good things about this. So this is the number of triangles divided by the number of triples. So let's explain these things, and I guess I've said some of it. Let's go through them in some detail. Right, so C1 is the average fraction of pairs of neighbors who are connected. So we're averaging across nodes. So here's a tiny little example network. So let's work through this one. So you see A has one friend, and so they can't talk about a socialness. So they'll get a 0 for their clustering. C has two friends who know each other, so their social world is complete, so they get a 1. B has 3 friends, but this A doesn't know C or D, so as far as B is concerned, their view of the world is that 1 out of the 3 possible friendships around them exists. So they get a local clustering of a third. And C and D are the same, they're symmetric. So that's this little picture down here. So clustering for A is 0, clustering for B is a third, a clustering for C and D is 1, the local clustering. And then you average over all of these, so they get an equal weight. So 0 plus a third plus 1 is horrible. I asked you an adding up thing. 2 1/3, and so it's 7/3, and then we could divide by 4 because there are 4 of them, and we get 7/12. So that's the clustering for that network, right? So you have a local clustering, and you get the average of the local clustering. And then you might, so of course we're going to think about networks with bazillions of nodes. What you'll do is think, well, if we had the same number of nodes and the same number of edges, and we made a random version of it, what would that clustering be like? Right? So now you have a baseline to compare it to. That's a basic thing to do. So is it very different from a random network? So what's your intuition for random networks? We're just going to, one way to think about it is we reach into a box, pull out a network that's got, the box has, on the side it says n nodes and m edges inside it. Pull one out. We talked about how these will have a Poisson degree distribution, which is interesting. What's the clustering like for a random network? So they're random. It has the sense that you want, which is that if you look at any node, I mean, one way to think of it is there are different ways to realize random networks, but essentially you are connecting randomly to other nodes. You could give someone a degree from a Poisson degree distribution to start with, or you could give them a probability of connecting to everyone else, a P, and let them flip a coin. All right, think about that. What would the clustering be like in that kind of network? And of course, it depends on the size. Okay, so that's the statement we had on the previous slide. Yeah, and we're averaging overall nodes, so I had this kind of average thing. So it's 1 over n, the sum of all of the local clusterings. So okay, so it's a simple little thing. So this is just a way of quantifying an aspect of a network and then comparing across networks and so on. We'll see this was vital for the whole small world story. Okay. Triples and triangles, this is a fun thing to do as well. So these measures don't match up. That's important. They are kind of weird how they behave relative to each other. They both end at 1. So if you truly have complete clustering in your network, it's then you'll get a 1. If you have none, then you get a 0 for both of these clustering measures. So what can you tell me? So what sort of network would have clustering of 1? What's going to be happening in that network? Yeah, so you could have right. So you can have something connect. You could have a node. You could have a fully connected network, clustering of 1. You could also have one that's a broken network, but it's full of exactly the same story, which is. Did I get that right? Yeah. All these little fully connected components. Yeah, that's right. So that would work too. So that's one limit. And then there's all sorts of possible ways to arrange nodes so that locally there's no clustering around any of them. There are no triangles. Locally, the important thing is they look like branching networks. Right. There could be some bigger loops, and we'll talk about that with random networks. The random network stuff goes on forever, so we'll dig into it a little bit. As much as we need to get intuition. All right, so we'll talk about a triple in a network and a triangle. So a triple is simply any, it's really, you can think of it as a chain of length 2. So this is a triple here, for example. So A, B, D. So it's any triple like this, right? Whether it's closed or not is irrelevant. So B, C, D is another triple. So you can think about one of them being a center, right? So C is the center of a little triple B, D, B, C, D. So here it is broken into its triples. We have A, B, C. I hope you can see this, A, B, D. And then there are 3 triples around here. Right? So each triangle is going to produce 3 triples. Right? There are 3 triples associated with this triangle. So that's an important feature. And of course, the only triangle here is present is that one. So what's going on? So this C2 is 3 times the number of triangles divided by triples because each triangle closes 3 triples. So from a counting point of view, that's why we have to put a 3 on the top. So for each triangle, we have 3 times the number of triangles, gives us the number of closed triples. So really what this top line is saying, it's the number of closed triples divided by the total number of triples. So much excitement. Yeah. Okay, so that's what this business is. And you'll hear, right, the fraction of transitive triples from social network analysis, right? Everyone has their own set of words. Good. Good. All right. So I think I've said these things. Oh, yeah, you can do this. Okay. Yeah. Yep. So you can have fun with a little bit of linear algebra, which is always fun, right? It's just fun. Yeah. Different calculus, which is merciless. Okay. So if right. So if there's that little path ijl, which I said was a way to think about a triple, then you have, well, okay, so here's a simple thing. Iaj, ajl equals 1. This is the ijth entry in the adjacency matrix, the jl entry in the adjacency matrix. So 1 times 1 equals 1. good bit of math. Otherwise, if both of these links are missing, or one of them is missing, then we have a 0 here, or both of them are 0, and we get a 0. So we can profit from this little business. We want to make sure that we don't come back, right? Because this would be a bad triple to count. We're trying to find, because we're thinking about whether this triangle is closed. So if this is I, J, and K, we don't want to go from I to J and then back. That's not a very good triple. That's a dopey triple, because we can't then think about closing that as a triangle either. Okay, so if we get out some machinery, it might do the wrong thing. So because it's just matrices and they're having fun and they don't care that you're talking about a network, they live in their own little world. Heads. So let's see. So in fact, so you can generalize this, right? So if you have all these nodes, so it starts from I1, ends up at IN, and you have a path that goes from through this sequence of nodes, I2, I3. This is very exciting. Then for the product of these guys is equal to 1, because you have a 1, a 1, a 1, a 1, a 1 equals 1. So you can think about multiplying. This is one contribution to the product of the adjacency matrix, which we're thinking about symmetric ones at the moment, right? Undirected things. Adjacency matrix, capital A times capital A times capital A times capital A times capital A, right? So it's how many, the entry you end up with in I1, IN, in that A to the, let's call it A to the N. Do I have the right thing? A to the N minus 1. That, and I know I'm just talking a little bit, adjacency matrix, so A to the power of N minus 1. That's the number of paths between whichever node you start, whichever row you start at and column you end up at. Okay, we could come to that. It's not shortest paths, it's just number of paths where you just wander around randomly walking. Okay. Anyway, so that's sort of a little detour. But we can just take the adjacency matrix squared and take the IL entry of it. That's what this is, right? So for fun and profit. So A squared, the ijth entry of that guy is from the definition of matrix multiplication. So it's the sum of K, and that's, am I going to use the wrong thing? I am. So let's make it IK, J. So Aij, AJK. Right? So it's the, if we look at the matrix, we have, this is the ith row and the jth column. And this is, the kth column. This is J going across, indexing across here, J indexing down this way. So it's the inner product of these two things, this column and this, this row and this column. And what you're doing is you're saying, okay, I'm going to start at I, end at K, and then all the possible intermediate, right? All the possible intermediate nodes, right? So they could be connected. You could get to K through all of these intermediate friends. And then there are some, maybe you connect out here and connect out here, and there are other nodes for which you're not connected if we're just thinking about the neighbors of K and I. Right? It will count how many ways you can get from I to K. Yeah. All right. So the number of triples, so that's just for I to, well, I've done L now. I've done L. Oh my God. I've done L. So that's just the number between I and L. Then we have to sum over all the entries in this matrix. That will give us all the ways to get from one node to another node through an intermediate. But we've also counted, this is funny, we're counting these ones that go out and then back to themselves. So we don't want those. So that's the trace of A squared. Detour for you guys. All right. So that's our number of triples. The number of triangles, we can think of it like this. It's a sixth of the trace of A cubed. Why is that? So this is the same story here. A cubed, each, yes?
Are we also counting ones where it simply stays at the initial point?
If it has a, okay, so we're assuming there are zeros along the main diagonal. No self loops. You're right. Yeah. Self loops matter sometimes, yeah. Good. Like it? Yeah, no, you're right. So if you had some stuff along the main diagonal, you have to be a little careful with that. But the one thing that we have dealt with is that you could go out and come straight back to yourself in this path. Number of triangles, it's a trace of A cubed. So this works, we don't have to do any corrections because to get back to yourself after 3 steps, wow, you have to go hop, 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 right? You can't come back to yourself. You can't do any returning to yourself. That's just going to be excluded because if you come back to yourself, the next step will be away. So the only way to get back to the initial node is, it's right, so it's the trace because now it's this. Okay, it's good. Yep. Cubed. It's the trace of this guy. So we can think of this as A, I, J, A, J, K, A, K, I. And it's a sum over I and J and K. So what's this little mess I've written here? So it's I has traveled to, you've started at I, gone to J, and then you've gone from J to K, and then you've gone from K to I, so it's back to where you started. And so this is going to be exactly what we want, and then you can see this is really A times A times A, and then because these two match up, it's the trace. Why do we have a 6th? We have a 6 because we could have gone this way, or this way, and we could have started at 3 different points. So we've counted the triangle 6 times. So put a 6 out the front of it. All right, so a little bananas, but you can take your adjacency matrix, do these things with it, and compute the clustering. And you can kind of see, so it's a cube power, so that's a little bit of a complication. Sparse matrices, not so bad. Am I going to keep this? Okay, right? A little bit of extra pain for you there.
Does that mean that we have square, we have it over 8?
Yeah, so right. So you can start to count larger cycles.
I was thinking we could go this way,
The-
or that way, we could start using.
Yeah, the problem with squares is, of course, now you can start to, yeah, it's okay. I mean, you just have to think about what you actually want. Yeah,
I see.
yeah. And triangles are good because that around each node, that's exactly what a little social wedge is a triangle. It is the right essence. Okay, a little bit of, if you like linear algebra, you'll be thrilled with that. If you don't, you're like, no. Anyway, it's cute. Look at that. It's very nice. Okay. Okay, last few things about this. So if you think about how these work, so sparse networks, which are often the case, this C1, the Watt-Strogatz measure, will discount really well-connected nodes. So each node is each node has some number between 0 and 1, and that's what it contributes, and then you average over all of those. So you could have some super connected node, it's got 1,000 friends, 10,000 friends. It just gets turned into a number between 0 and 1. Its clustering is something between 0 and 1. So it's given a equal footing to a node that has 1 friend or 2 friends, right? So it's going to discount their piece. So C2 will get all those triangles. It loves all those triangles. So it's going to be more accommodating for these well-connected ones. And as we'll see, lots of networks do have these well-connected nodes in them. They're not always the same. And just to think of what they are. So C1 is a global average of a local ratio, and C2 is a ratio of 2 global quantities. So, yeah, they're fun things to play around with. All right. The first one was kind of pragmatic. It's like, we need to, somehow quantify the clustering of this thing. And we talked about what the limits would be. So, well, a little bit. We talked about the fully connected thing. That's super social. All your friends know each other. You're in this little cult. And this doesn't happen at school. And The other extreme is none of your friends know each other, and that's a 0. So you know, you want to, this means you have some measurement you can apply to a network that will give you some idea of clustering. All right, so the other pieces we won't go into as quite as much. I think I have basically a page for each one. So Motifs was a piece that emerged, I think it's, when did this appear? So this is 2002, no, 2002, Nature Genetics. So, very nice idea. So people had been looking at these big scale patterns, so some of you might know about these sort of things, right? So the first work found 3 so-called motifs in biological networks. So they're, well, what were they working on? Gene-gene interactions?
Yeah.
Yep. Yep. Biology knowledge. Okay. So it's nice how it works, right? So X is being turned on for some reason, and that will promote Y. Y gets excited, so it starts to ramp up, and then that helps Z get going. But X also helps Z get going. So it's a feed-forward loop, so it has a delay in it. So that's a motif. This kind of structure. So now we're talking about directed networks. And they're dynamic. Obviously, there's something moving through it. But so as X goes up, then Y goes up, and then Z can go up. Even though X is trying to turn on Z from a start, there's a little delay time. So if X stops, it turns off the tap to Z, and so it turns off straight away. So it has a slow turn on and a fast turn off. And the analogy you could give is elevators, right? So you put your hand in, you want it to stop straight away, but the other way it can have a nice delay. It takes a while to warm up. Now, we'll get into this with random networks. You could just find this, of course, in a biological network. You just go and find it. You can find it in electrical circuits. We have kind of made them, of course. But the question is, do they appear disproportionately or in a way that's interesting, that nature is somehow producing these things in a more preferentially? And so it turns out yes, because what you can do is take your gene network or whatever it is. It could be a food network, food web. You can take all sorts of things, any kind of network you want. And then we'll come back to this later on. But here's the idea: you break all the connections. So you take out all the nodes. So right, we're going to break all these connections off, and we're going to pull this guy out, and then we're going to break all these ones off and pull it out. And then so you have all these little nodes hanging around with little stubs hanging off them, and then you randomly rewire everything. So you're going to preserve the degree distribution. These nodes have labels. This is Fred and Karen and Smithy, right? They all have names, so you can't shuffle them like that. X is still X. So they'll still connect and be connected to by the same numbers. So you preserve the degree distribution, which we have said is a big deal. But you've randomized everything else, and you have to be a little thoughtful about that. But you've randomized everything else, and then you can do that a ton of times, right? So now you can make a whole batch of networks that match exactly in the degree distribution and the specific degrees, right? So if Karen has 15 friends in this network, then all of these model networks that you've kind of these randomized versions, Karen still has 15 friends, but it's all been randomized, right? So then you look at the other properties of the network. So you can look at clustering, for example, what's happened to the clustering. So you've got the real one, you've got this one example of the real one, and you can make a bazillion of these others. And so you get an ensemble of them to look at, and you can get nice distribution kind of behavior. And you look to see if you have an anomalous aspect to your network. Right? So you're saying degree distribution matters a lot. Is there anything else about this apart from that is non-random? And so this is an example of something that popped out. These little of the possible motifs involving 3 nodes. The feed-forward one is one that presents routinely. There's also kind of a master switch type motif. So there's one node that turns a lot on or off. So at least in this original paper, that was seen disproportionately. And then another one, which is just sort of a mess. So lots of nodes, lots of other nodes, they go, and that happened unexpectedly. It's a hard problem to actually search through and say, I want to look at all possible motifs of size 3, of size 4, of size 5, because of this whole combinatorics business, right? So as you get an explosion of possible configurations of nodes, even up to 10, even 10, it's a disaster. There are lots of ways to put 10 nodes together. So some work had been done on that early on. Chris Wiggins, who was a colleague of mine at Columbia, he's still at Columbia, but he's also the head data scientist at the New York Times in his spare time. So he did some very good, thoughtful work trying to extend this mathematically, get it to work properly. Okay, another big piece that comes out of networks is they're not just a big blob, although they often are if you just sort of render them straight away. You have to think about it a little bit and come up with an algorithm, and so there's an enormous, this is just, it's ridiculous. So structure detection, this is a plethora of papers, just a sea of them that have appeared starting around about 2000, 2001. This is from Aaron Clausett, who's at Boulder. Mark Newman's done a ton of stuff on this. And a number of other people, Jim Bagro, who's here, had a paper in Nature on structure detection, and he did the very clever thing, right thing, which is looked at edges, which I've talked about a little bit. If you look at edge space, it's all on the edges, and came up with some very nice changes. Now, this has been going on in computer science for a long time. Like, how do you find if clusters in your data? There's lots of different methods. Networks sort of framed it slightly, people working on complex networks framed it slightly differently, but there's a lot of crossover. This is one where you know the story, right? So it's NCAA football, you know who played whom. It's pretty, 100,000 people went to watch that game, so it's pretty clear that happened. So you've got a good test bed here. Lots of examples like this. So you stuff your network in, all these interactions, and of course this is a temporal network, something to think about as well, but we close it down, we just say, all right, those two nodes are connected because they played a game this year. And here's an example coming out of this paper that found the local, what are these, divisions and so on, conferences. They actually popped out the right kinds of structures. That's interesting. No, I don't want to snooze it. Eat some chocolate.
I can't eat almonds.
You can't eat almonds? All right, you're in a lot of trouble because this is just basically, I'm just paying you off. Yeah. All right, I'll find something else for you. Yeah, if you're allergic to almonds or chocolate.
No, it's all nuts.
Okay, well, I'm just saying allergic to chocolate, that's pretty sad. Yeah. My commiserations for you. Anyway, I'm sorry. Yeah. Allergies are fun, yeah. Spicy food, actually my throat closes over and have to call the police. Lips will turn blue. Yeah, not good. All right, so I've just given you the way to get rid of me. All right, put a jalapeno in the cornflakes. Let's see, so my children, I hope, yeah. We have a loving relationship. All right, so they're going to be teenagers soon, could get bad. Okay, so have to be careful. Right, so this thing worked pretty well, and you can see all these other interactions are here. They've been downplayed because these have been found to be the stronger interactions, so they've been highlighted more. Just keep eating them, keep awake.
Chocolate's good for you.
Yeah, very good for you, especially at 1:30 or whatever it is. Okay, so this is a giant body of work, and we can. I talk about it more in the complex networks course, but you've got this big unstructured mess, and you want to put it into some algorithm that'll pop out and it'll show you, oh, here are the big clusters. Look at that happiness. The sort of thing you might be able to find is, oh, there are 4 big components here, right? And you can't see because you've got 100 million nodes. I mean, it's hard, right? And then within one of them, there are 3 big components, and so on and so on and so on, right? So this is structure detection or community detection, or another terms. And it turns out that a lot of networks, natural networks, have this kind of feel to them. Or, this kind of structure. Then there's even more on top of this, which is that, modularity is the other term, right? So there are modules, and there are modules within modules. That modular networks there are arguments that evolution has produced modular networks because they're more adaptable, right? So evolution if things are working out, will produce evolvable things, except for the platypus. So, yeah. Yeah, and you need some clever things though, right? You need some big switches so you can change the overall size of something, for example, right? You don't want to have a whole bunch of disconnected switches that say, make the liver a little bit smaller and then the femur has to be, that would be really bad, right? So there are some big dials that kind of have popped out. Concurrency, now this seems like, should be completely obvious too. And we talked about it a little bit with the kissing network, right, from that high school. Often, we present a network and you look at it and it's like, oh, look at this, it can spread everywhere. But there's actually it's accumulated data. So obviously contact for a lot of contagious things, it's actually about touching or being in proximity. Simple models often just throw this away, so it's a dynamic property, and it just took us a long time to get out of static networks. We're just figuring all these things like struggling around with clustering and sortativity and so on. So you need to know which, of course we do this practically with epidemiology, right? So there's contact tracing. So if someone appears with Ebola or they've become a zombie, then then the CDC arrives in the hazmat suits, grabs the zombie, and then they're harder, you can't ask questions of them. So but say they've got Ebola, you say, who have you been in contact with? It's okay, the zombie thing is not true. So whom have you been in contact with recently? And they have an argument about who and whom, and then eventually they get a list and they go and talk to those people. And they say, hey, I'm just going to wear this hazmat suit while we test you. Right. And that can really work out. All right, so we know about this, but obviously practically, but we like to simplify things. That's nice to have a little network you can put on a screen, so we accumulate the data. We record all the contacts between people over a year, and then we just make a network out because it's just too hard to study it. This is early work. This is Kretschmer and Morris, 96. I think that paper was in which venerable location? Yeah, it was in. Oh, okay. Well, I know she had a paper in Science. Anyway, so. Temporal networks is the big deal. So 2013, it took a long time, but now you'll see papers appearing everywhere in physics like, oh, we have more fun things to do. The soccer ball squirted out and they jumped into a thing that says, the ball says temporal networks on the outside. So they're happy again. But, this is craziness. All right. Okay, this is for branching networks, and we're all sitting here with branching networks inside us, right? The whole blood network thing, which seems to matter. So this predates complex networks, but these networks are all over the place. These are talking about river networks here, but they could equally be blood networks. So there are these branching network ratios, and so you can imagine, so there's an area, a drainage area, or it could be the volume of U that a particular part of the network supplies. As you go up in scale, and I go into this in the next course, I suppose, but you can think about, well, there's sort of an area here, there's an area here, and you can go across orders. You can define orders in a reasonable way. So the quick way to do it is to look at all these little streams at the outside, all these are sort of the edges of your network, prune those characters off, and then we've got this structure, right? So we've taken all the dash ones off, so we'll call them ones. Prune these ones off, because now we're sort of doing this renormalizing, these look like ones again, so we'll prune those ones off. We'll call them twos, and then what's left is a 3. And you keep going. So depending on your resolution, the Mississippi might be a 10 or 11 or a 12th order structure. And then you can look at, well, what's the average length of these little guys versus the length of these guys versus the length of these guys, and you get a fractal story, right? You get a scaling story, which will come to that kind of scaling later on. But the lengths scale in a robust kind of way, the number scale in a robust kind of way, and so does the volume or the area. So that seems to be true of a lot of natural branching networks. And it matters, so river networks are in 2D, we're in 3D, so we'll get to that when we talk about supply networks and scaling a little bit later on. Right, so that's important. And this actually, so Horton was the first person to talk about this, and he was let's say geomorphologist, a geologist, thinking about water and surfaces and so on, in 1945. So didn't say, Mandelbrot's the one who came up with the word fractal, but this is one of the very early quantifications of this self-similarity of natural structures. Everyone loves fractals. And it's still an argument as to how these things actually form and what their numbers should be for their scalings and so on. We can produce beautiful fractals, but explaining them is still a little bit of an issue for physicists. All right, there are a couple of other pieces in here, network distances, and then we'll start on models, which is fun. So shortest path length. This will matter for the small world business and for lots and lots of work that's done on networks. So we have two nodes, I and J. What's the shortest path between them? You know, a good question is, can they find it? Can electrons find it if it's an electrical network? You know, they usually don't actually. So it's simply the fewest number of steps, and you can imagine a weighted network as well. So you can think about traffic, right? How do you get from A to B, which is it might not be the shortest distance. There's, you know, could be you're there. You think about time, and of course that's it depends on in traffic, for example, depends on congestion right now and so on. If people are looking at leaves, you know, it becomes harder. So going back in time, you have chemical distance between I and J. This actually comes out of polymer science, which is funded by the plastics industry, which you've seen The Graduate, right? One word, plastics, which defined a lot of statistical mechanics for a long time. All right, so that's between two nodes. And then we can just take the average shortest path length, or the average path length for a network, just averaging over all these guys. And there are good algorithms for this. We're not going to talk about them just now, but we've sorted out by computer scientists a long time ago. And weighted links can be dealt with, right, with these fast algorithms. So that's groovy. You know, and if you think of it, this is a slightly hard business because you actually have to go between every pair, and there are n choose 2 pairs. So you don't want to sort of, you know, you could, if you just really started at node 1 and then went to node 7, node 1 and then went to node 8, you're doing a lot of extra computation. So there are clever ways to you know, reuse things. All right, or service a lot of calculations in one step. Okay, so that's a couple of kind of network distances. One is just a specific, and then there's sort of an overall measure. So when you talk about a small world network, right, that's going to be the story here. How big is the network in terms of what's the average path length between nodes? Sort of an idea, right, of smallness. Network diameter. So it's just simply the maximum distance. So this is a much more brittle kind of measure because you could have a clump. Your network could be some clump, and everyone's connected to each other, and then you have some tendril out here, and now the network diameter is long, right? It's large. If this gets broken, it drops. It's a measure. It's something to measure. It's been used in papers that have appeared in Science and Nature years ago, so I'm going to put it there. Closeness. So we talked a little bit about networks where you might have different components, and they're separated. This is a somewhat peculiar way, and I think this is the last of these measures. This is a peculiar way to try and handle that aspect, because if you have now, let's say we've got our network and it's actually disconnected into clumps, then if I is here and J is here, then the path length between them is infinity, right? You could say it's impossible to get from I to J, and it'll end up, it's bigger than any distance you could imagine, so it's infinite, right? So one idea is to take, instead of measuring the average shortest path distance, measure the average of the inverse. So this is a little peculiar. So 1 over dij, of course, in this case, will be 0. So you're averaging these guys, and all of the infinities just contribute 0 to that, so that's not so bad. And then you flip the whole thing back up. So it's still, if distance is measured in meters or cubits or parsecs, then it's still in the right things, and so distance is also growing as well. So this is sometimes called closeness. It handles this problem of disconnected networks. So if you start, it at least allows you to compare across networks. It doesn't give you a real distance, but You know, if you start to add links to this thing, then the average, the closeness will go down. So instead of just having infinity, 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 because there are some in here that have, you actually get a finite number and you can compare things.
And connected to itself is one, right? Or
Connected to itself, yeah, so, well, I guess it just depends on what you want to do with that loop. You could do something with that, yeah. Right, but generally speaking, we think of ones, well, it depends. But a lot of networks don't have a self loop, don't have self loops in there, and there's no contribution there.
I was wondering if like genetic regulated, right?
Yeah, okay,
That's
yeah.
like the most common motif actually.
Yeah, self loops, yeah, right. Yeah, yeah, so, I don't know if this is even a useful thing in that case, because they're all connected, right? I mean,
Well,
I mean,
effectively you get like a power line distribution.
yeah.
Of connectivity. I mean, you like genetic regulatory, that's straight on line.
Yeah.
So that's
So we've been talking about those things for a reason.
yeah.
I know you love them. Good. So this has the nice property that only when all the nodes are isolated. There are no links left in the system. That's the only time you get infinity. So that's not bad. So it takes a system, it gives a system that has some connectedness and maps this to a finite number, right? Whereas the average shortest path measure, which we quite like because it really is average shortest path, will just say the average shortest path here is infinite. And it wouldn't distinguish between, you know, a network that's like this and then a network where there are all these extra connections between these neighbors. They will all have average shortest path of infinity. So it allows you to sort these things out a little bit. That might be useful in some cases. All right, let's not worry about it. Centrality. Okay, so this is being important thing. It really first comes out of social networks, being studied in sociology. Centrality. So here's a sort of a sequence for this. So there's degree centrality. So here's the first simple thing. It's what humans do all the time. Someone has lots of friends, they're cool, they're important, right? They could be a leader of a cult, which is kind of a problem, right? So how does that influence go as you move out from that initial person? Okay, but that's a start. So that's a measure of importance. Here's a much more, a bigger one. So this is of course local. It's just a local measure. This is something that's global. So betweenness, right? This is a real word. I just listened to a whole podcast about between you and I. It was great. It's totally great. Well, between you and me versus between you and me. I know you're excited. All right. Anyway, great. So betweenness is actually this thing. So there's a node betweenness and an edge betweenness. So node betweenness says, all right, find all these shortest paths, and this can be done. All of this can be done in a fast way on top of this. On top of just finding the average shortest path length, you can also find this betweenness thing. So this is Greek. So find all the shortest paths, and every time you have a shortest path, so we've got some network, let's make it a bit of a blob like this. I'll put a node in here. Every time, so here's the shortest path between I and J, say. Right? K is on that shortest path, so they get one bean for being on the shortest path. So go through all the shortest paths, and every time K is on a shortest path, it gets a bean. Lima bean. Okay, so it's lima beans, and then you count up, and then you can look across the spectrum of lima beans, right? And this one over here is never on anyone's shortest path. It's on the end. Depends if you want to count the ends. But it doesn't lie between any other nodes, so it's not important by this measure. So betweenness gives you how central are you to the whole system. That can matter. And then also bridge type nodes will have a huge betweenness. Let's say this is a little isthmus here, and it's really just like this. Right? Then all the shortest paths for all the nodes in here and all the shortest paths connected to here all have to go through this character. So, this is not a bad measure for saying that they're important. Certainly if you remove this one, you fracture this network very badly. Turns out this is has been used very profitably in the structure detection business. Right? Because there's a way of there's clearly sort of two big parts to this. And one way to get at that, and I'm just going to say quickly, is to compute the betweenness for all the nodes, take the node that has the highest betweenness and remove it. If the whole thing falls apart, then you say, okay, now I've got two pieces. Then you recompute the betweenness over and over again. You don't use your original calculation, you recompute the whole thing, and then do the same thing. Pull out the biggest one, right? So, if this was actually a bridge involving 4 nodes, right? Then, actually what would happen, let's say we just had 1 node here. So this would have the highest betweenness, it's gone. It gets taken out in the first range. These would all have the same, so they'd be removed sequentially, and now you've broken it. And now you can see, oh, there really were these 2 big pieces. And then maybe this guy has this kind of blob shape like this, and you start removing more and more. Eventually this will splinter, because they'll be the nodes with the highest betweenness. And that's a way of finding the modules. Again, lots of different methods for doing this. There is a whistling. Okay. Do I have a nose whistle? Not yet, a few more years. Okay, so, yeah, young people. So let's see, so we can do an edge between us as well, right? So we can do the same thing. Instead of, well, we're leaving a lima bean at every node, but we can also leave a pinto bean along the edges. So each edge, how much, this is very much like traffic, right? So how much traffic, if, and this is the odd thing, right? In this betweenness calculation, you're kind of saying every node wants to send something to every other node uniformly, right? Which is a bit odd. What's the actual dynamics on the network? Well, so it's very stylized and kind of made up. You're imagining all these things are moving around constantly. That this node wants to transmit stuff to everywhere else. It could be messages, for example. And this node wants to transmit to everywhere else. And they're doing it every time step. They're sending off all these packages. So you just let it happen. So this is another way to think about it. You let it happen, and you just see how many packages are at each node, at each time step. This one has, once it settles down, right? At some point, it's going to be a steady stream. Once you get your package that you're receiving, you take it out of the system. Eventually it saturates, and a node might be getting 40,000 packages that it has to then distribute. This one that's out here doesn't ever get any. It sends and receives, but it's never transmitting them, so it doesn't have any betweenness. All right, so that's good. Yeah, good. But it is a bit odd, because that seems a strange imposition or sort of statement to make about a network, that it's doing this big message passing thing. It's usually going to be some more restricted level of that. And there are other versions, so hubs and authorities. So there's John Kleinberg, he's this MacArthur Genius fellow at Cornell, brilliant guy. Thought of this at IBM, I believe, is the story. There's a paper you can find on this here. Called it Hubs and Authorities, very clever thing, linear algebra business. So the idea is that nodes have content. You can go to them, so think about the web, right? So Wikipedia actually tends to be a good subset example. So each Wikipedia page has content, obviously, but also can have links to other places. So that's their hubness, or their hubtasticness, or hubbishness, right? It's how much they point, how much they signpost you. And then authority is how much content they actually give you. And the idea is that good hubs point to good authorities, and that's recursive, and this keeps going. And so the original story for Google is basically the same idea. I carried it out in a very efficient kind of way, but that's, again, recursive, global idea, but and now it's specific to a particular search word, which is very clever, but this was a smart idea for finding what's the most central, the most important, the most influential, or yeah. But it's actually a bigger story, right? Because it's going to be some distribution of things that are valuable. I think he was working at IBM at the time. I think this is a story, IBM and kind of like the coder to Indiana Jones and Raiders of the Lost Ark, right? So where they put in a box, they pretty much did that. So that's cool. Maybe we can license that. We have good people working on this. Meanwhile, that whole Google thing took off about the same time. Anyway. Okay, interconnected networks. So we talked about temporal networks taking off. This has been a big hot topic recently. It's obviously true, but of course you can go back and see work being done back in years and years ago, but it's become something that people have worked on extensively now. Raisa D'Souza, who's at Davis, actually we graduated next to each other at MIT. She's done a bunch of work on this. Paul Hines, who's here, has worked with her and others on this problem. So the example here is here's Italy's power grid overlaid by a communication network. This is a very stylized toy model version. It actually really, lifts away from the real problem, but nevertheless, nature absorbed it. And so the interesting thing is that you can have networks that are robust to certain kinds of attacks on either side, but if they're connected in certain ways, the whole thing can be unstable. So it's opened up a lot of fun for the piranhas, but it is a very real story, right? So often you have many things overlaid, right? You have transportation, you have the gas delivery system, like natural gas, and you have electric, power grid, communications, all those things are overlaid. And so there are analyses of cities to find the really, obviously by good guys and bad guys, to find the locations that are the most sensitive, in the sense that many networks are could be imperiled by taking out a particular place. Or if there was a failure, an accidental failure, or maybe a giant marshmallow man stamps on something in one particular place, that's going to be bad. Okay. Okay, all right, so complex networks, it's the late 1990s, ridiculous number of papers. I mean, it's just absolutely overwhelming, and you can't read them all. But it really made the whole complex systems business much harder, and I've shown you just a little bit here. And when we talk about these networks, so we're not really thinking about graphs in the tradition of graph theory. They're typically large-scale sparse. They can be synthetic or natural. This aspect, evolving and dynamic, that's clearly what all of them are, but that's been a very hard thing to capture. But it does mean certain kinds of networks exist and many others don't, and they're measurable, and that's opened it up, right? And we had these kind of blurred lines, categories, but the sort of very physical ones, they're hard to dig up and move around. Interactional ones, where there's costs associated with them, are really, there is a burden in maintaining a link or moving a link and so on. And then ones that are more abstract, where it might be hard to change the meaning of a word, for example, but it feels like no one's using power doing it. Anyway, that's, bit of a hard argument, perhaps. All right, informational kind of things at the end. Okay, so let's start the next bit. Well, you know what? We've got 5 minutes. I guess we can say a few things. Yeah. I'll just tell you what. I'll just give you. So we'll stop, but I'll give you the just sort of the outline of where we're going to go, right? So first of all, we're going to talk about generalized random networks. So I've said random networks have been a lot of fun. They live in mathematicians' heads. It's a good place to be. And all of them have, invariably have, if they're large enough, they have a Poisson degree distribution. So you never find any of those in the real world, but you can add a little bit of, play around with this a little bit. We talked about it exactly with the Motifs story, where you say, okay, I want random networks that have this degree distribution. Everything else is going to be random. So let me build those and then play around with those. And that turns out to be quite powerful. The motif thing is exactly an example where it's used. But you get a lot of good stuff out of that. Things about spreading, contagion. You can solve non-trivial problems on them, and get a sense for how things might spread, might break. So these are quite useful. We'll get into then small world networks. So there's a sort of an unfolding story here. I mean, this is work that I was part of in the early 2000s, and it starts with Watts and Strogatz in the late 90s. But there's been more work done in interesting ways, because it's a small world thing, right? So the small world phenomenon, 6 degrees of separation. It's got a very nice story, Kevin Bacon game. So how do you get from any arbitrary actor to Kevin Bacon by saying that these actors were in the same film? So there's a parlor game version there, and you can talk about, your friend knows this person who knows this person who knows this person who knows Obama, or whatever it is, right? So people have fun with that. Doesn't mean you can have influence, of course, through these networks. But it turns out that this is a social search problem, right? So it's a search problem, and it also informs how, this is an odd thing, right? So we have bio-inspired computation, but this is socio-inspired computation and architecture. Like, you could structure networks or look at informational networks in a different way, thinking about how people solve information searching problems in organizations and in some of these stylized small world experiments. So we'll talk about that. So lots of good things. And then there's a way here to think about real social networks, lifting out of these generalized ones. And then scale-free networks. So this is a whole business, and we will see a reprisal of, is that the right word? We'll see the rich gets richer story will reemerge, because it itself has a rich gets richer thing attached with it. Well, it's the truth, so that is also kind of an issue. That doesn't always work for you, right? In fact, I was just sort of musing about this, and I put out a tweet that didn't get too much hate. It got some interest, which was, so mistruths, so we can stop about this, but mistruths around a truth are so abundant, right? There's so many. So you have your true story. It's this sort of one point. Here are all the facts, which is a difficult thing, obviously, disputed sort of thing. But let's say something really did happen. Then you have all these possible stories that are adjacent to it, and it's just, there are so many ways you can be around that story, or have these adjacent stories. There's so many possible versions that, and many of them will be terrible, right? I don't know, like JFK conspiracies are a huge thing, right? So JFK was shot by an android raccoon. That's a bad story, right? That's a terrible story. You can just make up all of these terrible stories that are nearby, which are still laden with truths that people agree on. But then you can have ones that are, you can have many of them that are quite appealing for whatever reason, like all sorts of possible. And because there are so many adjacent possible other stories, the chance that one of them sounds better and does better than the true one, I don't know. I think it is sort of is up there, right? It's one story. There's the truth versus a bazillion mistruths. However slight they may be in the way they change away from the truth. So it's a stiff competition. There's the actual real story, which may be a little boring, and then you can just kind of inflate it nearby, and people will spread that. Anyway, it's about why there's that whole notion of lies spread very easily, which is debatable. Anyway, that was a little spin out of it. I think it is all about stories, actually, right? Equations are stories, algorithms are stories, and then our stories are stories. But so we'll get to that later on. Anyway, this is where we're going next. We're going to dig into these very famous works. As I said, 20,000+ citations for these things, so kind of a big deal. That's hard to do. If you get to 10, you're like, yay. My paper is awesome. Someone else read it. You got cited by a robot. Okay. All right. Okay. I will always bring chocolate. Deal? You just have to eat it. All right, people. Oh, yeah. Talks.